Hello guys, this is Sanjay and welcome to my channel. In today's video, we're going to discuss about quantum physics. Okay, so in quantum physics, we're going to discuss about mathematics intuition about it, all the mathematics derivation. Okay, in there we're going to discuss the first thing is about probability. So what's probability? Probability is nothing but the chance of something happening. And in quantum mechanics, we use probability a lot. Like we have the probabilistic nature of wave particles and etc. So what is probability? Okay, before that we'll discuss about mean. So what is mean? Mean is Fi(xi), you have learned in 10th grade, by Fi. Okay, sum of the frequencies into the term, okay, the class interval, and multiply by this. Okay, so now class interval like 1, 2 and 3, 4, 5, 6. Okay, so you have 4 types of 1, you multiply them and divided by 1 by 5. This 50. Okay, sorry. So this is the value. We can also represent it as this. Okay, sum of j, same thing, and number of j. J is the term, xi, number of terms. Okay, divided by the total number of terms. Now you can see here this thing is probability, number of favorable outcomes of j divided by total number of outcomes, or this summation of Fi. Now we can represent it as probability. What is this probability? Now we have j pj. Okay, this is the formula of mean or average, if you want to say. Now we can say for any term it is let us don't put it f is j. Sorry, for any term j it is fj into pj. For j square it is this. Okay, so this is a well-known theory, I guess, a well-known formula for mean, that a function, you take a mean of it, is equal to summation of its function into probability. So from this we can obtain this. We also have a concept of j square. This is different from this. It says j square inside, this is j square outside. So this is summation of j pj whole square. And if you take sigma, standard deviation, which is equals to this. Okay, this is also a very nice result, outcome, a formula which is very famous of standard deviation. Okay, now we had some intuition of probability and mean. Now let us do something. This was for discrete functions. Okay, discrete means like this. It has some gap between it. It is continuous. Okay, so for discrete functions we have summation, for continuous or integration. So if you represent it as a continuous function, we have this fx, mean of it is equals to the same fx or probability of that same x or fx. Okay, and dx. Okay, this is the general formula. If you remove fx for now because of it is causing confusion. So let this be the general formula: x px is equal to dx. Now one more thing is this is known as Bohr's interpretation. Okay, this is known as Bohr's statistical interpretation, which says integration of sum of all probabilities is equals to 1. Like if you have a graph, probability distance graph. So area of this entire curve, I've told you in my Newton video that integration is about area from negative infinity, this side, positive infinity. The area of all this sums up to be 1. Okay, this is what is known as Bohr's interpretation. Not Bohr, Bonds. Sorry for that pronunciation mistake. Okay. Now, in quantum mechanics, we don't represent probability as this. Why? Because they know how to represent it in a fancier way. So we represent it as psi square. What is psi? Now, you know what is intensity is proportional to amplitude square, right? Similarly, we can just say it's equal to probability is equals to psi square. Okay, this acts like the amplitude of the wave. Like we don't know what is this. I actually know physicists knows what is psi. Yes, they just say call it as wave function, but we don't know what is the physical meaning of wave function. So its modulus squared is nothing but probability. Okay, so here we can replace px by this term. Okay, now we have this. So this is Born's statistical interpretation. This is nothing but the formula of x. Now we will learn that this is nothing but operators. X is the positional operator, and then we have also momentum operator. We'll learn this little later when we are done with Schrodinger's equation. So this is about Born's interpretation. Now we'll go to the most awaited part of quantum physics, which is Schrodinger's equation. Okay. I hope I didn't miss anything. Yes, I know. So we have Schrodinger's equation. Okay, let us derive it using a simplified, oversimplified way. Okay. Now we know one thing, that total energy is equals to kinetic energy plus potential energy, right? This is standard energy conservation. Now let us put kinetic energy from momentum. This is simple high school physics, and let this be a function of x. Okay, potential energy be a function of x. Now what you have to do is that we know waves have often formulas, like wave function especially has a formula e to the power minus I kx minus omega t. You know, this is similar to what is that your Euler's identity, which is e to the power I theta is equals to cos theta minus I sin theta. Now, see, this is nothing but you can see they are similar. This part, okay, this part, the complex part, okay. Now we know this is also similar to a wave formula. What is the formula? Yes, sin kx minus omega t. So there you can see all of them relate to each other. Like e to my minus kx minus omega t, this Euler's identity, and then we have this form here. So they all relate to each other. We can put theta as kx minus omega t, and then you can get this actually for sine and cos. Okay. So this is how they relate to each other. Okay, what is wave function and this. Okay, so please note it down. So now we have talked about what is wave function. Like we know it is like kind of wave, but you can see it's like how can I describe it? You have collection of waves, like how a wave is existing. Like it is somewhat like amplitude, and then squaring it gives, instead of intensity, it gives probability. So intensity is nothing but how much chance you have if you have probability, and amplitude is somewhat like the side wave function. So we need this information. Okay, so this we can talk about in other video about Euler's identity, and if you want about wave, we can talk about in other video. They are very huge topics. We have wave optics based on this, and we have entire complex mathematics based on this, complex analysis and all that stuff based on this thing. Now we just need this formula for now. A E power minus x minus omega t. Okay, now we know, I have discussed about de Broglie's formula, and we also know about Planck's formula. Now, what is this f? C by lambda? What is lambda? From here, we can say lambda is 2 pi by k. K is a wave number. Okay, wave number, which is proportional to 1 by lambda. Now, putting this, we get momentum is equals to h. Okay, and then we have divided by k. Sorry, 2 pi k. Okay. Now, in physics, we have a term for h by 2 pi, which you'll see a lot in Schrodinger's equation. We term it as h cut. H by 2 pi is h cut. Now, we can put this also as h cut, and we get h cut k. Okay, E is h cut k. So from here, we can get k's value, which is here, which is nothing but wave number, is h cut by p. Now similarly, we can do this. We can find the value of omega. What is omega? Omega is 2 pi by f. Or we can just represent it as omega is v by r. Okay. Now we can say, sorry, omega is v by r, that's correct, but omega is actually 2 pi f. Sorry, not 2 pi by f, it's 2 pi f. Now, what is f? From here, f is equals to E by h from this formula. Okay, f is equals to E by h. Now, putting the value here, we get w is equals to 2 pi by h and then E. Now, we again have h cut in inverse. So, from here, we get the value of omega. Omega is equals to E by h cut. Now let us erase this. I hope you have understood that energy conservation part. Now, what you can do is plug these values of these both here. How? Psi x is a e to the power minus I. K is h cut by p x minus h cut by x. Oh wait. Wait. I think I have kind of messed up here. I think it's p by h cut, not h cut by p. This is a mistake here. I think again derive it for you. K is 2 pi by lambda. Lambda is h upon p. And then yes, we get this formula. Okay, so if you didn't understand, okay, I'll just do it again for you, because we know that K is equal to 2 pi by lambda. Okay, now what is lambda? Lambda is h by p from the de Broglie's identity. Put this here to get 2 pi by h into p. Sorry. Now we know what is 2 pi by h. It's h cut in denominator, so we get this. Okay, sorry for that mistake before. Now we take here we have why is this not okay. Now you take h cut common, and we get is px minus et. So we get a formula for xi x in terms of energy and momentum. Now I hope you know what is differentiation. I've taught about the basics. It is something within the slope. Here, you might be wondering where the slope here. So it's basically we are going to take the derivative of it. Why? It's like, the Schrodinger's equation is a derivative form of this energy conservation. So that is why we're taking derivative to derive it, obviously. Now if you derive it with respect to x, this is partial derivatives. Okay, when you have multi-variables, this is partial derivatives. Here it is not x, it's xt. Okay, that is what it is. As the function psi is dependent on both x and t, as you can see here, the function is dependent on both x and t. So that is why we're going to take a partial derivative, which means it is the derivative of this with respect to x. You can just remember this as this is here it is just taking the t part, the other variable as constant, and then finding the derivative. Here it is the derivative of this is a e. Now here power minus I by h cap. Now here what is the derivative? Derivative of bx minus et. Now this is constant. This goes to 0. Okay, this comes entirely, but this thing goes to 0 while taking the derivative here. We get p here. Okay. Now if you do it twice, one more time. Okay, you get p square a square. Wait. You get p square a e to the power minus a h cut px minus et. You get this. I hope it's clear. Let me just check once. Oh, my bad, I forgot to take this out of here. So it would be like, so it would be like, this comes here, minus I by h cut, and then what? I don't know what it meant. Okay, so here also this thing will come down and become minus I by h cut whole square. So this will be nothing but d psi by dx square is equals to what is minus I square. It is minus 1, which is p square by h cut square, because minus I into minus I is equals to minus 1. How? Because this turns to positive I square, which is minus 1. This is all complex number stuff. If you want, I can make a video on it. E to the power minus ah cut px minus omega t. Sorry, et. Now we can take this as z. So this thing is equals to minus p square by h cut square and z. Now let us put this here, this thing here. Sorry. Okay, my bad. So let us put this here. Okay, transpose this here. We get, and then negative sign also here. Okay, minus h cut square, and then this d square psi dx square is nothing but minus p square psi. Now what? You can see this is somewhat related to momentum. Okay, so now let us divide by 2m, because this now looks like kinetic energy. This is exactly the form of what we need as kinetic energy. Okay, so this is kinetic energy, part of the equation. So we know it's minus h square by 2m d square plus I by dx square. Okay, take the photo and then I just need more space, so I'll just erase this. Okay, so let me just write the result here. Minus h square by 2m d square psi by dx square, and nothing but the kinetic energy part of the equation. Now what we do is we take the time derivative of this dx minus et. Okay, time derivative of this is same, but we have e here. So e I by h cut, sorry, you have h cut, we have minus I by h cut e, and then we have a e to the power minus I px minus et. Now again we want to take this as psi. We're going to take this as psi. Now we have e, so we have equation for e. Let's take this here, and this is nothing but this comes down, so it turns h d psi by dt divided by minus I. What is inverse of minus I? If you multiply this by minus I by minus I, you get here I square, which is minus 1, and then we got I. So this is equal to I. Okay, let me just trap this in the box. Okay, and then far away in the island. So we touch it. So yes is nothing but E psi. And then we, after doing some, conjugate stuff, the conjugate means, multiplying by its own self in numerator and denominator. Like you have learned, if you have an irrational number, to rationalize it, we just multiply by its conjugate, which is root 2 naught plus root 3. and then we get root 2 plus root 3 divided by minus 1, because it becomes 2 square, root 2 square minus root 3 square, which is 2 minus 3, which is minus 1. So this is how we do it in complex numbers. So from here we get E psi is equals to I h by d psi by dt. We have one more result. Now what? We're just missing one thing. Potential energy. None. Now add them. Now let's add them. What we get? This plus this is equals to this. So this thing by this dx squared plus b psi equals to I is d psi by dt. And there we go, Schrodinger's equation. We have just derived it using energy conservation law. Okay. Now, you can just take the solution of this derivation. Now let us do time independent form of Schrodinger's equation. Okay. What is that? It is like where we don't have time. We're independent of time. Okay. Now, let us take. Wow, what is that? Psi in the form of psi x. This is capital psi, this is small psi. We just differentiate between them. This is nothing but a function, smaller function. This is nothing but the wave function. This is also a wave function, but it's a function with respect to x. This is function with respect to x and t both. So it is this and then phi t. Okay. Now what we'll do is let us let's differentiate again. Is psi by dt. What we get? Okay, this is constant, so we get this thing psi x, and then we take the d psi by dt. Similarly, we do for this. Okay, let's do a single derivative first. Like t, and then we have d psi by dx, and we take one more time. We get d square psi by dx square and psi t square. If I'm right. Okay, my bad. This is just this. Okay, so we're taking this derivation and then we're differentiating this with this. Okay, level differentiating. Okay, so here we just take this as constant, and then we take differentiation with this. Okay, so this square term won't come. Now we can plug these terms in our Schrodinger's equation. So what was our Schrodinger's equation? Minus h squared by 2m. Now we add this term here, so we can just put this here. D square psi dx square plus v psi remains itself. So psi also we have psi we have to put this one. Psi x this is equals to, let's say, is I h cut and this term psi x d psi t divided by dt. This is the thing. This is after you plug it. Now, just take this part. Okay? Why I'm taking this part? I'll tell you. Now, this part, just separate this. Okay? Just take this part, okay? Why you say? I'll just tell you in a while. We know this term is equals to energy. Okay. So what? So what indeed? And what can we do here? E psi. I'm not wrong. It is equals to E psi. Before that, well, one more step before that. We just divide the entire equation with psi and this thing. 5. Divide by this thing and this thing. So we have dividing by psi t, psi x. Say phi t, psi x. What we get is minus h squared by 2m, and we have 1 by here, yeah, the 1 by which is psi x d square psi by dx square plus v, but this both cancel out, is equals to I h cut 1 by psi t d psi by dt. Yes, this is what we wanted. Now you do is let me do it here. Here you just take this right hand part, okay, 1 by phi t d phi by dt is equals to e. Now I just had it better. I h cut 1 by phi t d phi by dt is equals to e. This is equals to e, okay? Energy. Now what you do is take this here and take this here. We get d psi by psi is equals to e by I h dt. Integrate both sides. Power, nice integration symbol, right? We get log phi is equals to e to the power et divided by h. Okay, not e to the power, because this are constant, it comes out, and then this is dt. Integration of dt is only t. Now we just take exponent both sides. Okay, same. Now what we get? This is nothing but this is cancels out. So we get phi is equals to e to the power, this becomes minus I on top. So we get minus I e t divided by h cut. Okay, now let us put this in this equation. Why? Because then we get a Schrodinger's time independent equation. Okay, put this value of that here. Okay, now we'll get is xi x is equals to this thingy into e to the power minus I e t divided by h cut. This is a time dependent equation of Schrondinger. Independent. So I'm just saying dependent is independent. Okay. Now let's talk about operators. The last topic for today. So we have seen that formula, right? This one. X is equals to integration of this x psi square dx. Now what is x here? This is nothing but known as operator, positional operator. Okay. Now what you do is, if you just take df by dt, which is mv, okay, momentum, m dx by dt is nothing but v. Okay, x, we take this inside, x I square dx. Okay, we get this. Now, before we move forward with this concept, we have one more concept. That xi mod of xi square is xi into its conjugate. Xi star is nothing but its conjugate and xi. So we can just break this down here, and after solving, okay, shall I show the solving? It is actually a complicated solving. Minus infinity to infinity. Oh yeah, it's gonna be very bad. X differentiating the respective this thing with x psi star psi dx. Yep, it's gonna be a bad one. Okay, let's move this here. There you go. This is not pleasant. It's not pleasant, okay? It is going to be a big one. I'll show you some steps. Using the product rule, we can just say this is equal to xi star d psi by dt plus xi d xi star dt. This thing. Now, we can, from Schrodinger's equation, we can find the values of this. I'll tell you how. Separate these terms. How? You can separate these terms, and then first you find this, because we have that d xi dt in that right hand side, where we write I h cut d psi by dt, that the energy term, and separate it out, and then take its inverse, which means just inverse the complex stuff, like just take it minus it, like you have minus h square by 2m, just take it as h square by 2m. That's why you just take it as minus v. Okay, so after all that stuff, and then plugging all that stuff, okay, plugging the value we get from this, from the equation, we plug it here back, and then we have some normalization. Okay, I'll explain normalization first. Normalization says in a graph of psi square x, the graph form is normalized when at infinity this thing turns to 0. What turns to 0? This. Okay. What was it? Yeah. Relax. Basically, the wave function turns to 0 at infinity. Xi star slash psi is equals to 0. Okay, this is a normalization. We just plug this in. We just take it into 1. So we just take this stuff into 1. The Bohr's interpretation, as I told you. This is what does normalization. We just normalize this, okay? So you're doing all that normalization stuff here, like after cancelling out some terms, and that we get the final momentum operator to be what do you say? We get for the momentum, okay, no, the average momentum to be minus infinity to infinity, okay, and then we have minus h d by dt xi square dx. I hope this is correct. Minus h d by dt, and then we have wait, it's minus I. Sorry, it's minus I. This is the momentum operator. Now, this, if you want a video, I can make a video on deriving the momentum operator. Like, this is average momentum, and then from that we'll derive the momentum operator. So as we talked here, this is the position operator, this is the momentum operator. It's minus h squared d by dt. So the general form of any operator let's take it as h is equals to the h cut xi square dx. or we can write it as the mean of this is equal to minus infinity to infinity h dash xi dash h cut xi dx. Okay, this is the operator general formula of operators. This is the operator. This is also known as Hamiltonian operator. So we can take it as any letter, but I kept h purposefully so that I can explain what is Hamiltonian operator, which is nothing but that term. Which term? E psi term. E psi is equal to h psi, the most famous one. This h psi, this one, minus h square by 2m d square psi by dx square plus v psi. This is your Hamiltonian operator. Hamilton. Okay. And then what's left? Nothing. I think this is for today. We learned about probability, mean, and then how to derive Schrodinger's equation, time independent equation, and operators. So if you want that momentum thingy, which is actually very deep, and then I can make a separate video on momentum derivation, Unfresh theorem, and then what? Anything left? No. I mean, till here we have only two major things which is left. I didn't discuss in this video, which is the momentum derivation and Unfresh theorem. Unfresh theorem is nothing but I'll just show you. It tells you that minus dv by dt is equals to the force. Okay, this is Unfresh theorem. So we can derive it also using the same things because it has many conjugates and that stuff. If you want derivation, I can give you. Okay, till then, goodbye. Thank you.